hitting record. I almost always hit those buttons. I don't even know which Facebook account it would connect to, or YouTube, because I don't have this, my school email connected to anything. All right. Weird little side note, but thought you guys needed to know. We are going to continue with chapter 20 today. So let's see. I'm trying to think of what other things we talked about at the beginning of the other class. I did do some grading this weekend. I'm definitely behind on grading compared to what I would like to be, what I normally am. And so I'm definitely going to be spending time this week catching up. I've actually been taking a class myself. I've been taking an online teaching certification class. And I've been doing like all of my classwork just on Tuesdays. Like I've dedicated my Tuesdays to that since the semester started. But that's done. So I can actually, I've essentially like gained a day in my week. So I should be able to get grading done a little bit quicker and get caught up. I think that's it. I'm trying to think. I think that's all we talked about at the beginning. Okay. And I did not write down what slide we ended on last time, but I'm pretty sure this is the last slide we did. We filled in the boxes as our last one. Is that correct?
Yes.
Thank you. Justin, I don't know if you're trying to ask a question or if you just left your mic unmuted, but it sounded real weird. So I don't know if you were trying to say something or not, but if you were, I did not hear you or understand you. It sounded like you were, yeah, it sounded like you were in fast forward, but also like a Mickey Mouse voice. Did you have a question? It did sound alien-like. It might not be Justin. It might be an alien that's taken over. Is this slide 38 to everyone else? The numbers are a little bit off because sometimes as I lectured, I added in some blank slides so that I could show some mechanisms. So in my own notes, like when I wrote the slides, it originally was number 36. So yes, it was 36, but then because I've added in some blank slides to show some extras, yeah. All right, we shall continue. So we've talked about carboxylic acids, we've talked about acyl chlorides, we've talked about acid anhydrides. So we're halfway done with our functional groups. What we have left are esters, amides, and nitriles. And we might not finish today, but we'll definitely get pretty darn close. So we're starting with esters. And I'm going to continue to give us little stars for ones we need to know the mechanisms for. And I will, morning class did finish, but they were actually a few slides ahead of you guys for some reason. It just kind of happened that way. So they did finish, but we are maybe like 4 or 5 slides behind them. It happens. So we're going to start by making some esters. So we're starting with our carboxylic acid, and we're going to do this reaction twice, once under basic conditions and once under acidic conditions. So this one is basic, and then this one is acidic. So starting with our carboxylic acid, we are adding in some strong base. So we don't really care about that sodium part. We care about the hydroxide. We care that it's a strong base. And the strong base's job is to take off the hydrogen of that carboxylic acid. So essentially just make it into a carboxylate. And then we are adding in an alkyl halide. So this is shown as a methyl group, but really it just needs to be an alkyl halide. And because we are doing an SN2 mechanism, that alkyl group would need to be methyl primary or secondary, no tertiary, nothing too bulky, because this is really what's going on. Nucleophilic attack, loss of a leaving group. We've seen this. This is not a mechanism you need to know for this chapter, for this upcoming test, because it's one we've done before. So it's not unique to this chapter. And then in the second reaction on this slide, oh, we're making an ester. Let's put that over here too. In the second reaction on this slide, we're also starting with a carboxylic acid, and we're going to react it with an alcohol. So I'm even just going to write this as ROH, be a little bit more generic there. And the H plus on the arrow is our acid catalyst. And again, we make our ester. We talked about this mechanism. I'm going to go back a whole bunch of slides. We talked about it here. So obviously it's not on this slide because my notations go away. But when we first learned about the mechanism steps and the generic mechanisms, this was the one I used as an example. So it is slide 19. Oh, I see your comment. Let me read it. Just 1 second here. Normally when we work with halides, it's bromine or chlorine. So a lot of times we don't use iodine because it's too slow to react. So you're right. Normally we use chlorine and bromine. They're kind of right in the middle. They're good middle of the road halogens. Fluorine is usually too reactive and iodine is usually not reactive enough. But in this case, we don't want to have too good of a leaving group because we don't want to end up with this. Oh, sorry, this should be a positive. The other line didn't show up there. There we go. We don't want to end up with a carbocation floating around because then that will react in a different way, or it could react in a different way. We want the oxygen on our carboxylic acid to kind of be the driving force for that reaction. So we're using a leaving group that's not a great leaving group to prevent that from happening. Bromine and chlorine could still be used in this. It's just going to change like the speed of the reaction. It's going to change that reaction rate. So if you saw the same reaction with bromine or chlorine, it's going to give us the same product. Good question though. The last little note on this slide says that we also learned how to make an ester when we started with acyl chlorides and we reacted them with alcohols in a pyridine solution. And that was in section 20.8. So that was a couple slides ago, probably last Wednesday. But we did talk about how to make them that way as well. Okay, let's see. I'm looking at my notes here. You might want to look up something called the Finkelstein reaction. Oh, good tip. So where we're headed with these now is how to react our esters. And again, the esters are kind of the middle of the road in terms of reactivity. So they need a little bit of help. And that can either mean acidic conditions or basic conditions. And so we're starting with turning our esters into carboxylic acids. And we're going to do this under basic conditions. And then on our next slide, we're going to do it through acidic conditions. And you do need to know the mechanism for this one. And we have the mechanism on the bottom of this slide here. So we are starting with a nucleophilic attack. That hydroxide that is in there is going to attack our carbonyl carbon. So we have our nucleophilic attack. Pi electrons become a lone pair. That's our tetrahedral intermediate. The OR group isn't normally a great leaving group, but because we're in basic conditions, it is. So when we have negatively charged oxygens or nitrogens, they are good leaving groups under basic conditions. So we get the loss of a leaving group, the OR group takes off, the pi bond reforms, and so we get our carboxylic acid product. Notice though that in that second step of our reagents, we have acid and water. Even though we've made our product, there's other stuff still happening. So we're in basic conditions. So this is showing that OR group. It could have also been a hydroxide ion that's doing this step. Under basic conditions though, that carboxylic acid is going to get deprotonated. And so we end up with the carboxylate ion. And so that last step, which I'm going to add in here, is another proton transfer. So we're going to grab the hydrogen from that acid and water, and we make the carboxylic acid. So that last step, that acid and water, would be a workup step. So that would be an acid wash. So like an HCl acid wash when it's in that separatory funnel. So essentially just to make sure that everything has all of its hydrogens in place. So, and to neutralize anything, because that acid wash would also neutralize the leftover basic solution. Questions about that mechanism at all? Okay. And we can do the same thing under acidic conditions. So this is still our ester to our carboxylic acid. Acid and water as our reagents. We're going to make an alcohol as our side product. So this is just the leaving group that's coming off of that ester. But it can be easily removed. We have a carboxylic acid as our product. So while it is still deprotonated, we can leave it in the water layer and then use an organic solvent to remove that alcohol. So essentially using those ionic properties and different solubilities to allow them to separate. We're going to give this guy a star. It is the opposite of the Fischer esterification. So the one that I mentioned that I showed you the mechanism for on our first day of this chapter, that's the Fischer esterification. This is the opposite. And I think I have, oh, I have it on here. I was going to say I thought I had a blank slide for it, but it is on here. We have acidic conditions. We have a neutral nucleophile. We have a poor leaving group. So with all of that in place, it means that there's a lot of proton transfers. So that's exactly how it's going to start. We're starting with a proton transfer because of the acid catalyst. So we're adding a hydrogen to that carbonyl oxygen, and then we're doing the nucleophilic attack. So remember when we first talked about these mechanism steps, the nucleophilic attack and the loss of the leaving group were the only mandatory steps. And then this list of proton transfers, acid catalyzation, bad leaving group, and neutral nucleophile are the reasons why we would have these extra proton transfers. So our nucleophile in this case is water. We do our nucleophilic attack, and then we get our first tetrahedral intermediate. The next proton transfer is happening because of that neutral nucleophile. So we're taking the extra hydrogen off of the water molecule. One more proton transfer. This proton transfer is to make the OR into a better leaving group. And then we get to have the loss of a leaving group. So our OR group, now it's an alcohol, and ROH group leaves. We reform that carbonyl bond. And then in the last step, we do our proton transfer. And this is also because we have the acid catalyst. So this is to remove the acid catalyst. And so it is just reforming that H3O plus ion. It's giving us our acid catalyst back. So this one, and essentially going the other direction, going from a carboxylic acid to an ester, are showing us the maximum number of proton transfers, showing us all the proton transfers. They're just doing it in opposite direction. So going from the ester to the carboxylic acid or vice versa. Any questions about this one at all? Okay.
Professor?
Yeah.
Whenever the word hydrolysis is used, is that just does that just mean it's under acidic conditions?
No, it doesn't really have like a specific definition. It really just means that there's water involved. It means that we're adding water to a molecule, which is, and the reason why I say it doesn't have a specific definition is because in this case, we are just, like if you look from start to finish, we're really adding an OH group to the molecule. That extra hydrogen is getting removed. It's just kind of a generic way to say that there's water involved in the reaction, though, because we also use the word dehydrate, but that doesn't always necessarily mean that we're removing H2O. It means that we're removing an oxygen and two hydrogens, but they don't necessarily have to be together. So it's pretty generic. It just means there's water around.
Thank you.
Mm-hmm. So we can also turn our ester into some other stuff. So we can turn our ester using an amine into an amide. And our amine here has the same rules as our other ones. So meaning it has to have a hydrogen attached. So we could use ammonia, we could use a primary amine, or we could use a secondary amine, but we can't use a tertiary amine. It has to have that hydrogen attached to it. And I'm looking at my notes here, see if I need to, I do need to star this one. So you do need to know the mechanism for this one as well. And the second one that's on here is the Grignard reagent. And for the Grignard reagent, again, we have our ester, we have excess Grignard, and we've talked about the excess word before. It could just be abbreviated as XS. We're going to react it twice, so you might also see it as 2 times or 2 equivalents. It's written out a bunch of different ways. But we have our Grignard there. And then water in that second step. And as we've talked about and you learned about in lab as well, that water does have to be a second step. Otherwise, it will react with the carbanion of the Grignard. But our product for this will always be a tertiary alcohol. So it has the carbon group that was already attached, plus the 2 R groups that we're adding on. And it's not going to create a stereocenter because the 2 R groups will be the same. So we'll always have some amount of symmetry to it. And then I have our mechanism here. Oh, I have a blank spot for it. Okay. In my notes, it just says mechanism. I couldn't remember if it was one I needed to draw in or if it was on there. So there's my ester. The Grignard is what we would consider to be basic conditions because the carbon itself is negatively charged. So we have a lot less proton transfers. And we've talked about that there's a couple ways to draw a Grignard reagent. So if we were going to use an ethyl group, we could write it like this. So we could write it as that carbanion. The other way to write it, to make that look more like bonds, is to leave it attached to the magnesium and the bromine and write our nucleophilic attack from the bond. I think it's actually more common to do it this way. I think our book might prefer the anion version, but if you're looking up other resources, I think it's more common from what I've seen and what I remember over the years. I think it's more common to do it this way. So if we leave it bonded, our nucleophilic attack is going to come from the bond. And so that's telling us that we're breaking the bond between the carbon and the magnesium, and we're forming a new bond to that carbon. And then the other thing we need is we're going to move those pi electrons up into that lone pair position. Nope, not what I wanted. What happens when I touch my stylus for too long in one spot? There we go. That was weird. Okay. You always want to make sure you're counting carbons. So I'm going to go back here to my original structure and just count 1, 2, 3. 1, 2, 3. And then we'll count what we added. So 1, 2, 1, 2. And when I use the phrase counting carbons or tell you to count carbons, it doesn't mean you're counting them in a way that would make sense for naming. And you might not count them the same way I would. You're counting them just to make sure that the amount you're starting with and reacting with is the same as what you're ending with. We don't want to lose anybody or gain anybody that's not supposed to be there. So it's really just kind of a bookkeeping kind of thing. You're making sure that you are aware of all the carbons. All right, next up, loss of a leaving group. So we're going to get our pi bond back, and that OR group is going to take off as a leaving group. And then again, we can double check our carbon count. 1, 2, 3. Those are my 3 original carbons. And then 1, 2. And this is going to react with that Grignard reagent a second time. So we're going to go right there. So a second nucleophilic attack. And then pi bond becomes a lone pair. So this would also be a tetrahedral intermediate. Do some numbering here, be consistent with my colors. 1, 2, 3. 1, 2. And let's do some orange. 1, 2. 1, 2. So at this point, with the chapter that we're in, we would want to reform the pi bond and lose a leaving group. But we don't have any more leaving groups, so this kind of puts us in the same scenario that we were in chapter 19. Instead of losing a leaving group, we're going to add in that water that comes in the workup step, in that second step, and we're going to do a proton transfer. So we're going to grab onto that hydrogen and make that alcohol. So we end up with our tertiary alcohol as our final product there. Questions about that mechanism, or, well, really about anything, but questions? Let's just leave it at that.
Professor,
Yeah,
is this mechanism supposed to be the same as the aminolysis one, or
no. So we can draw that one out as well. But
okay?
no, it's not going to be the exact same. Let's see. Do I have room over there? Let's put it up here. Well, let's do it in another color so it stands out better. It's an unwritten step. Does the magnesium bromide bond with the OH group created? Yeah, so the magnesium bromide would still be positively charged, and so it would bond to that OH group, yes. So there's my ester and my amine. We're going to do a nucleophilic attack. This is also considered to be under basic conditions. Ammonia is a weak base, but it's definitely more of a base than it is an acid. So we do still need a couple proton transfers. Well, one proton transfer at least. Because we're using that neutral nucleophile, we do need to get rid of that extra hydrogen. So I'm just going to use another ammonia molecule to do that. So we're going to grab onto that hydrogen, put the lone pair back onto that nitrogen. And H2. And then the last step for this one is to lose our leaving group. And again, because we're in basic conditions, that negatively charged oxygen is a decent leaving group. So we're going to reform that pi bond, kick off that leaving group. Oops. And then we get our amide as a final product. So a couple less steps than the one we just looked at because of those basic conditions.
Professor, I have a question.
Yeah.
So I don't know the exact slide, but I know when we were doing excess LiAlH4 with H2O for the mechanism, we use H3O plus at the very end, and then it becomes H2O. What would happen if we used H2O?
It would still be fine. The reason
Okay.
why we use, I'm just trying to find some blank space for myself here. The reason why we would write it as H3O plus instead of H2O in that scenario is because when we have that lithium aluminum hydride and we add the water to it, it's immediately going to make aluminum with 3 hydrogens and H3O plus. So the water is immediately going to steal any hydrogens away from that aluminum that hasn't already reacted. And so that's where that H3O plus is coming from, even though we're not directly adding in that acid. But yeah, if it was a test question and you wrote it as H2O instead, that works as well.
Okay, thank you.
You're welcome. Anything else on those few reactions there? Okay, so speaking of lithium aluminum hydride, it's exactly where we were headed. So we are looking at reacting our ester with our hydrides. So you do need to know the mechanism for both of these ones. Thankfully, it's the same. We've already seen it. So we're starting with our ester. We're reacting it with our excess lithium aluminum hydride. So we've seen this guy before. It's our 4 hydrogens bonded to our aluminum. That makes aluminum not too happy. It wants to get rid of not just a hydrogen, but the electrons that are holding it in place. And we're going to add 2 hydrogens to that center carbon. And so we are going to be making a primary alcohol as this reaction progresses. And again, it will always be primary because we're adding those 2 hydrogens. In the reaction below, we're using, so it's abbreviated as DIBAH. It does actually have a couple other abbreviations, but its name is diisobutyl aluminum hydride. So we have looked at a couple other ones on our acyl chloride and our acid anhydride. We looked at the tert butoxide ones. This is essentially doing the same thing, meaning we've added on these bulky groups onto our aluminum, and it's going to make it less reactive. So we have diisobutyl aluminum hydride. So it's abbreviated, as I said, DIBAH. Sometimes it's also just abbreviated as DIBAL. So it's, when we say it, we just call it dibol. Abbreviating it as dibol is definitely not the most accurate acronym. We're not like taking the first letter from each word, but it's easier to say. It makes more sense. So you might also even see it written as dibol with the H. They all mean the same thing. They all mean that there's 2 isobutyl groups attached to that aluminum with a hydrogen. This one is a little bit different than the other ones though, because there aren't 4 things bonded to the aluminum. There's only the 3. And so it is neutral, which means it doesn't have that lithium, or it doesn't have a cation to help balance out that charge. The mechanism itself is the same as what we've seen. It's just coming from a different source. The hydrogen's coming from a different source. And because it is less reactive, the reaction is stopping at that halfway point. We're going to stop it at that aldehyde. Do I have? Okay, I thought I had a blank slide waiting for me. So we're going to look at the mechanism for the top one, but I'm also going to kind of show you how that can be converted into the mechanism for the bottom one. So we're going to go from an ester all the way to that primary alcohol. So we're doing ester to primary alcohol mechanism. So here is my ester. There is my aluminum hydride. Actually, let's give that a little charge, make it accurate there. So we're going to start with our nucleophilic attack. So we're starting at that bond. Pi bond becomes a lone pair. We get our tetrahedral intermediate. And so at this point, we're going to reform that pi bond, and we're going to have loss of a leaving group. So if we were using the other aluminum reagent, that would be our stopping point. So if we started with this guy, if that was our starting point, that would be our product. Oh, I forgot an arrow in the middle there. Okay. So it's not as reactive because it's neutral and not charged, and because it has those bulkier groups attached to it, making it more sterically hindered. But we're using lithium aluminum hydride, which is smaller and charged, so it is more reactive. So that means we're going to do this again. So we're going to do another nucleophilic attack. And then in that second step, we're adding in water. And this is where you could write it out as water or H3O plus. Both work, both make sense. And we're going to use our lone pair to grab onto that hydrogen, do a proton transfer. And we will get our alcohol. And I am showing the hydrogens in here because we added them in during this reaction, but you definitely wouldn't have to. When we're doing mechanisms, I like to show all the pieces that get added in. Questions about this reaction at all, or this mechanism? Okay.
How would you, sorry.
It's okay.
How would you, for the diabol reaction, when we're doing the nucleophilic attack, how do you want us to like show them, like if we're writing the mechanism, do you want us to just write out the structure?
So like the way I have it drawn right now?
Yeah, so then just I'm gonna take it, like you draw the arrow, the bond between the aluminum and the H, and you just draw it as a nucleophile.
You can definitely do it that way. If you want kind of a shortcut way to do it, you could write diabol with a bond going to a hydrogen and do your arrow coming from there.
Okay.
So it's kind of a cheat way to do it, shortcut way. It works though. Okay.
Okay, thank you.
You're welcome. We have done our acyl chloride reactions. We've done acid anhydrides. We've done esters, which are at the same approximate reactivity level of carboxylic acid, which is where we started. And what we have left is to talk about our amides. This slide is to talk about how to prepare amides, but that's what we've done. We've talked about how to make them using all of these other starting materials. So starting with our acyl chloride, we can use excess ammonia. And starting with our acid anhydride, same thing. Wait, was that? Okay, making sure it was just NH2 on the bottom there. We could use excess ammonia. And then starting with our ester, we can use ammonia. So we know how to make our amide from all of our other starting materials. The most efficient way would be to start with the most reactive chemical. So starting with that acyl chloride, because it's the most reactive, it's going to give us the highest yields. Obviously, that might not be the option. It might not be what you're given on paper, or it might not be what you have in your lab. But if you do have a choice, that would be the best way to do it. So what we're going to look at in our next couple of slides then is how to react the amide. And one of the things that we talked about in the very beginning of this chapter was we can always turn something that's more reactive into something less reactive, but we can't go from something less reactive to something more reactive using a nucleophilic acyl substitution reaction. So it doesn't mean it's not possible. It just means we can't use that reaction. So that means we're going to need the help of some catalysts. And it also means that we're just going to see less reactions in this section. So we are starting by turning our amide into a carboxylic acid. And we're going to do it two different ways. We're going to use acidic conditions and we're going to use basic conditions. And we are going to look at the mechanisms for both of these on the next couple slides. So you do need to know both of those. So in our acidic conditions, we're starting with our amide. We're reacting it with acid and water. We're adding in some heat and we're getting our carboxylic acid. So not only do we have the acid catalyst in there, but we have the heat in there to help the reaction as well. And then when we're under basic conditions, we have our amide, we have our strong base, we have our hydroxide in there, we have some heat, and then we have acid and water to finish out the reaction. So we are going to go through the mechanisms for both of these. So we're going to start with the acidic one. So going from the amide to the carboxylic acid. So I'm going to write it as an NH2, but this definitely would work if you had R groups attached there, either 1 or 2. It's not going to affect anything. So this is under acidic conditions. So I'm going to start with my H3O plus up here. And we're going to start with a proton transfer. So proton transfer, and our reasoning for that proton transfer is because we have our acid catalyst. I always feel like the acidic-based ones become so tedious because there's so many little steps to do. We've done our acid catalyst. We're going to do our nucleophilic attack. So remember, the reason why we do that acid catalyst is it weakens that pi bond. And so our carbonyl carbon, the one with the partial positive charge right there, is going to have an even stronger partial positive charge because of that weakened bond. And that's going to make it a better electrophile. So we can do a nucleophilic attack on that electrophile. Pi bond becomes a lone pair. So here's our tetrahedral intermediate. What do we need to do to this thing? What should our next mechanism step be?
Do another nucleophilic attack on the water?
So not a nucleophilic attack on the water, but we do need to do something to that water molecule. We're going to do a proton transfer. We want to take away one of those hydrogens. So proton transfer, and our reasoning for that proton transfer is because we had a neutral nucleophile. NH2 is not a good leaving group when we're in acidic conditions. So we need to give it a hydrogen. So we're going to use some hydronium again and do one more proton transfer. And our reasoning for this proton transfer is to create a better leaving group. And now that we've made it into a better leaving group, it can be a leaving group. So we're going to have loss of a leaving group, and we can reform that pi bond. Last step then, we got to get rid of that extra hydrogen. So if we put that catalyst on in the beginning, the last step is going to be to take the catalyst back off. So one last proton transfer because of that acid catalyst. So we put it on, we have to remove it. But we've made our carboxylic acid. Questions at all about the mechanism, the reaction, any of that? Okay, then let's look at the same reaction, but under basic conditions. And this one definitely has less steps because it's basic. So there's just going to be less proton transfers needed. So there's my amide. There's my hydroxide. So the reagents for this one in the first step is hydroxide and heat. And the second step is acid and water. So right now we only have the hydroxide present. So we're going to do a nucleophilic attack. Whoops, that was a horrible spot to draw that. Let's try that again. We are in basic conditions, so our leaving group can be negatively charged. So NH2 is a decent leaving group when we are under those basic conditions. So we're going to have loss of a leaving group. Go that way. And we made our carboxylic acid. So why in our reagents, in that second step, we're adding in acid and water? What is the acid and water doing? Why do we have that step on there if we've already made our product? So it has two jobs. One of the jobs is that it's going to neutralize any extra hydroxide, which we wouldn't normally show in the mechanism. But the second thing that it's going to do is we're still under basic conditions. There's still hydroxide floating around. There's negatively charged nitrogens floating around. This hydrogen is not going to stay on that carboxylic acid. It's going to become a carboxylate ion because of the basic conditions. And so when we add in that water acid mixture in our workup step, it's going to put the hydrogen back onto our carboxylic acid. So if we're writing out the mechanism and including this step, it kind of seems redundant, kind of seems silly, because we take the hydrogen off and put the hydrogen back on. But really, there's kind of a divider line right here. When we're taking that hydrogen off, it's because it's still in a basic setting. It's in a basic solution. And then we put our solution in our separatory funnel. We add in a acid water solution. That's going to neutralize everything and give our carboxylic acid its hydrogen back. So it is technically doing something here, even though it looks like we're just taking something away and giving it back. If this was the test question, though, and I asked you for a mechanism, you would not need to show that part. You could show me that part, and it would be a complete answer. Even though those last two proton transfers are happening, they're essentially the result of our environment and our solution. They're not showing the production of the product. Questions about either of those mechanisms? So either of those amide mechanisms? Okay, we are going to fill in some boxes because this, oh wait, no, sorry. We have one more left and then we're going to do some boxes. One more. Excess lithium aluminum hydride. So you do not need to know the mechanism for this one. It's the first one in a while that I've been able to say that. But it's quite a bit different. So starting with our amide, we're adding excess 2 equivalents, lithium aluminum hydride. So we've talked about lithium aluminum hydride often. We've already done it today, but we know what it looks like. Water in that second step, and we're going to make an amine. What makes this one different from our other ones and why we're not looking at the mechanism is in our other ones, and let me go back a couple slides here. When we look at our ester reacting with our lithium aluminum hydride, this group, which in our first couple slides, we just kind of abbreviated that extra thing as a Z, that leaves. That's our leaving group. The carbonyl oxygen becomes the alcohol group. And that's what we saw with everything else that reacted with lithium aluminum hydride. With our amide, though, the nitrogen is still attached. It does not leave. It's that carbonyl oxygen that actually does leave. So this one follows a very different pattern from what we've seen with our other functional groups reacting with lithium aluminum hydride. So no mechanism for this guy. All right, let's fill some boxes in. I'm going to do some numbers here. So we have one amide reaction on here, but lots of esters. So what about that first box? How are we going to turn our amide into an amine?
With the excess LAH in water.
Perfect, thank you. And then looking at our ester, how are we going to make our amide? So for box number 2, we're going to go from our ester into our amide. How do we make that transition? So for that one, we're just going to use our NH3. What about converting the ester into a carboxylic acid? So box number 3. How do we make that transformation?
H3O plus.
H3O plus, perfect. What about box number 4? So going from our ester to this tertiary alcohol.
Should be the Grignards.
It is a Grignard. And how many carbons on our Grignard reagent should we have? So we're going to have our Mg. Oh, go ahead. Sorry.
Should be ethyl.
It is an ethyl. And I am just going to write it as an ethyl. So you could write it out with letters. We could draw it out with structures, but either way, an ethyl. And I'm going to do a little carbon count here, just in case you don't see the ethyl. So 1, 2, 3, 4 were the original carbons. 1, 2, 3, 4. So those are the 2 ethyl groups that were added on. So that's how we knew it was an ethyl. What about box number 5? We want to reduce our ester into an aldehyde. Diol, yeah. So diol, that will reduce it, but not fully. And then, so what about number 7? What if we want to go from the aldehyde down to the alcohol? So this actually would have been last chapter, but it is a reagent that we've used multiple times in this chapter as well.
Lithium hydroxide and water?
Lithium hydroxide and water. So not lithium hydroxide. We would have too many oxygens involved, but it is lithium aluminum hydride. Again, we like to go back to that lithium aluminum hydride a lot. Little dot there. And then, so speaking of lithium aluminum hydride, going in box number 6, so going from our ester all the way down to that primary alcohol, we're going to use that same set of reagents. We're going to use the lithium aluminum hydride and water again. So that's just a full reduction as far down as we can go. Question about any of the boxes? Okay. So we've talked about acyl chlorides, acid anhydrides, esters, carboxylic acids, amides. We have one left. Our last reagent, last functional group are the nitriles. And before we actually talk about the reactions for these guys, there's one thing I want to talk about just with some of the wording. So when we talk about a carbon bonded to a nitrogen as an ion, we refer to this as a cyano group, or if it was part of like a full name, we could call it a cyanide. But when it's actually part of a compound, we would say that the compound has a nitrile functional group. So it's cyano when it's on its own, and nitrile when it's part of a functional group. It's kind of like the difference between having a hydroxide, which is the ion form, and an alcohol, which is when it's in its functional group form, bonded to a carbon. So there are definitely some similarities, but the biggest difference is whether or not it has that charge or not. So if you called it a cyano, it's not, everyone's going to know what you're talking about, but it's not completely correct. So just a little bit of reminder, possibly brand new, just because we don't talk about this functional group often, but just so you know what the difference is between those two terms. So first reaction, we are making our nitrile. So we're in that preparation section. No mechanisms at all in this section. So we're actually done with mechanisms for this chapter. This first reaction, though, we are reacting our alkyl halide with a cyano group, and we're going to make our nitrile. And this is an SN2 reaction. So I'm going to kind of give us a little mini mechanism here, because we know our SN2 is a nucleophilic attack, loss of a leaving group. It's not new to this chapter or special to this chapter, though, so you don't need to be able to reproduce that. Our alkyl halide, because this is an SN2 mechanism, we need to have a methyl group, a primary, or a secondary. It's not going to work as well with tertiary. It's just a little bit too bulky. The sodium that's attached to that cyano, it's just cation. You might not see it written there. It might be a cyano with a charge, might be a potassium, definitely not as common, but it would do the same job. But we make that nitrile. One important thing to note about this one, and I'm going to say this a couple times for our nitrile reactions, but we add a carbon. We're adding in one carbon to this chain because we're adding on that cyano group. The carbon is part of that nucleophile. So it is literally just one carbon, but it's important to note that because I always remind you to count your carbons. And so in this case, we want to make sure that we know we're adding on one carbon as we do the reaction. And then the second reaction that's on here, we're starting with our amide. We're reacting it with SOCl2, which is thionyl chloride. We've seen this reaction before. Well, I'm sorry, we haven't seen this reaction before. We've seen this reagent before. It turned our carboxylic acid into an acyl chloride. So it's a pretty powerful reagent. In this case, we're going to make our nitrile from our amide. This one is referred to as a dehydration reaction, and so this kind of goes along with the question that came up earlier about hydrolysis, and I mentioned this term as well. It's called a dehydration because we're losing an oxygen and we're losing the two hydrogens. Notice that we're not making water as any of our side products here, but because of the atoms that are being removed, as a result, we label it as a dehydration. So it's kind of a loose term that we use, but it is a way to create that nitrile. So these are our two methods on how to make a nitrile. So now we're going to look at our couple of reactions on how to react our nitriles. And so we're starting with hydrolysis. So it kind of goes back to those words we were talking about. But we're starting with our nitrile, and we're going to make a carboxylic acid. So this is showing us that we're making an amide as an intermediate. So a more accurate way to portray this would just be, whoops, let's try that again. H3O plus would be to write it as just one step. That amide intermediate, we can't stop it at that step. So it is showing us that it forms, but we can't halt the reaction right there. I am going to show you this mechanism on the next slide so you can see where it's coming from. It might help you remember it or understand it better, but it's not one that you have to reproduce. And then the same thing with the one below it. So both of these are making carboxylic acids. The first one was acidic conditions. The second one is basic conditions. So we have our nitrile. We're reacting it with our hydroxide. We have the acid and the water in the second step, and we get our carboxylic acid. All right, so we're going to look at both of these mechanisms. Again, you don't need to know these for the test, but it can help you understand the reaction or even just remember it a little bit better. So here's the first one. This is the acidic conditions. So we're going from our nitrile to our carboxylic acid. And this is actually only showing us the first half of that mechanism. So it is under acidic conditions. So when you have acid, start throwing around some hydrogens. So we're starting with a proton transfer. We're adding a hydrogen onto the nitrogen, and then we're doing a nucleophilic attack. So one of the reasons why I don't have you learn or memorize these mechanisms is because they don't quite match the pattern of what we've done in the rest of the chapter. There's definitely some similarities, but we're not dealing with a carbonyl, so it doesn't look exactly the same. And I don't want learning these ones to add confusion to the other ones. So I bring that up because right now we're doing a nucleophilic attack. So as we do a nucleophilic attack on that nitrile carbon, the pi electrons become a lone pair. So there's definitely some similarities between what just happened here and our carbonyl mechanism steps. But obviously we're dealing with nitrogens, we're dealing with triple bonds, so there's differences as well. Proton transfer, just bringing it back to being neutral. Proton transfer, so our nitrogen has a lone pair on it. We're in an acidic environment. Nitrogens are good bases, so really this is happening because nitrogen's a decent base in those acidic conditions. Resonance. So we're just moving electrons around at this point because of resonance. in that second resonance structure, the positive charge ends up on the oxygen. And so because of that, we do a proton transfer and get rid of the hydrogen on that oxygen. And so here's where we make that amide. That amide is going to continue the mechanism to turn into a carboxylic acid. And this is a mechanism that we looked at. I was going to tell you the slide number, but I know my numbers on my notes don't match up anymore. We looked at this mechanism a few slides ago to show how that amide makes that conversion. And it was a long mechanism. It was, 6 or 7 steps already. So what's on the screen here is only half of that nitrile mechanism. So that's probably also makes you happy that you don't need to know it, because you don't need to know a double long mechanism. But that is how it happens. It goes through this big long process. And then in the second one, so same starting material, same product, we're going from our nitrile to our carboxylic acid, but this time under basic conditions. We start with that nucleophilic attack. So no proton transfers to start with, because there's no extra hydrogens floating around. So we are attacking that nitrile carbon. Pi electrons become a lone pair. Now we're going to do a proton transfer because we have that negatively charged nitrogen. And so we're making it neutral. Oxygen's hydroxyl groups are good proton donors, or good acids. And so because we're in acidic conditions, we're going to lose that hydrogen. So it's kind of the same idea as the last slide. Because we have that nitrogen and we're in those acidic conditions, it got to gain a hydrogen. It's the same idea here, just opposite reasoning. We get some resonance. And then in that second resonance structure, our nitrogen now gets that negative charge, which isn't as stable as having an oxygen with a negative charge. So then we do a proton transfer. And this is the same story as our last one. We make that amide as an intermediate, and then that's going to go through its own steps to create that carboxylic acid, again, under basic conditions. So we looked at this one as well. It was only about 3 steps that we saw when we looked at it a few slides ago. So this one wouldn't be as long, but you still don't need to remember this one for the test. It's just hopefully a way to help you see what's happening, or understand what's happening a little bit better, see where that oxygen is coming from as the reaction occurs. Questions about either one of these? Okay. Grignard. Everybody gets to do a Grignard reaction. So for our Grignard reaction for this one, we are going to add on 1 Grignard reagent. So just 1 time to create our ketone. So starting with our nitrile, reacting it with our Grignard, and we can make our ketone. Acid and water in that second step, so we know that that's there to quench the reaction, or another way to say that is to neutralize or react any of that excess Grignard reagent. And then in the, oh, I'm sorry, I put a star next to that one. I did not mean to. I just got in the habit of putting stars as we went through these. You do not need to know that mechanism. I think I just really wanted to circle it or something as I was talking about it, but no, you don't need to know the mechanism. And then the second one that's on this slide is a reduction. So again, starting with our nitrile, we're reacting it with our excess lithium aluminum hydride, water in that second step, and we're going to make our amine. So we're going to reduce that triple bond all the way down to a single bond and add in hydrogens all over the place. So our carbon of our nitrile gains 2 hydrogens, and our nitrogen of our nitrile also gains 2 hydrogens. Questions about either one of those? Okay. This is kind of what we've done. And I say kind of because this isn't all the reactions. This is in your book. It's labeled as a functional group conversion map. At the start of this chapter, I had mentioned that learning the reactions this way can be really useful. It can get really messy, as you can see, because obviously this is published, which means they did it as neat as possible, and it still looks busy and messy. But if you are able to do this on a piece of poster board or a whiteboard, or even just a piece of paper and writing as small as you can, it can be really helpful. And so this is showing us essentially all the functional groups we talked about in this chapter. It also has aldehydes on there. You could include a ketone on here from our last chapter as well. But it's really, we should be able to have a pathway going from any reagent to any other. And it might not be a one-step direct pathway, but we should be able to get there. Another way to work on this, remember this, is to create flashcards. So not with any reagents on them, but just have like 10 flashcards that have a drawing of a carboxylic acid, an acid anhydride, an acyl chloride, essentially all of our functional groups, and then have the same identical 10 in another pile. And then when you're practicing, just take one from each pile and come up with your own reaction, your own multi-step synthesis to figure out how to get from one to the other, and then figure out how to go the other direction. You should be able to convert any of these into any of the other ones. It might take you a couple steps, it might take you a handful of steps, but you should be able to convert any of them to any other ones. And then the other category of reactions, if this is converting functional groups, which focuses on the heteroatoms, mostly oxygen, obviously, the other half of the reactions, or I should say portion, it's definitely not have, but the other portion of the reactions are focusing on carbon skeleton changes. So there's always less of these in a chapter than there is the functional group changes, but this one is looking at how we can change the carbon skeleton. So on the left-hand side, we are using Grignard reagent. And so notice that this one is using the Z there. So that can be either, well, it can be any of our functional groups we've talked about. So whether it's a nitrogen, an OR, a chlorine, depending on which functional group we're looking at, but we can add on those two Grignard reagents. And then we looked at our Grignard reagent for our nitrile. The one that's in the middle here, do you remember what the name of that reagent was called? What the reaction name is? So that one is a Gilman reagent. And that one is useful because we are still keeping the ketone present, and it means that we can then continue to do reactions. So when we have an alcohol on our group, it limits what we are able to do. But having a ketone there, it leaves it with still that reactive center. And then the other two that are on the right-hand side are much less, they're much less severe in terms of how many carbons they're adding, but they also have a lot less flexibility. So both of these are only adding one carbon. So when we're adding on that cyano group to create that nitrile, we are adding one carbon to our chain. And then if we are doing a Grignard reaction to create that carboxylic acid, we're adding in that one carbon from that CO2 group. So both of these add on one carbon, which again is not a huge change, but it is something that you need to be aware of when you're drawing out what your product will be or what reactant it is that you want to start with. Questions about any of these? All right. Our last couple slides are practice problems, some multi-step practice problems. So we have a few minutes left. Let's see if we can work through these. If not, we can finish them on Wednesday. But these are literally the last two slides. So just a couple multi-step problems. So that first one, we're starting with an ester. We're going to react it to create a cyano group. So how I would approach this is I first would start by numbering some carbons. So 1, 2, 3, 4. 1, 2, 3, 4. So that tells me that I don't really need to worry about changing that carbon structure. I only need to worry about changing our functional group. And I don't know how to go from a carboxylic, or excuse me, I don't know how to go from an ester to a cyano group in one step. But any thoughts on how I could do this in 2 steps or how we should start it?
Can you reduce it first?
Sure. What do we want to turn it into?
An alcohol?
So we could turn it into an alcohol. We could use lithium aluminum hydride to do that, but I don't think that that's going to help us get over to our nitrile. So in the chat, I see that Uriel put to use NH3, which I think will help us get there. So if we use NH3, we can turn this into an amide. And then how can we go from our amide to our nitrile? And then the SOCl2. To that thionyl chloride. What about in our second one here? We have 1, 2, 3, 4 carbons in a nitrile, 1, 2, 3, 4 carbons in an aldehyde. So this one is not one step either.
Acid catalyst, H2O, and heat.
Okay. What's that going to make?
It's going to do carboxylic acid.
Okay, sounds good. And then can we go from a carboxylic acid directly to our aldehyde?
No.
All right. What do we want to turn that into then?
SOCl2.
Okay.
And then do the, what's that name? The lithium aluminum OR3. So just do O tert butyl 3H and then H2O.
Yeah, that big long name. So the tri-tert-butoxide aluminum hydride with the lithium. Forgot that in there. But yeah. Yeah, and there's definitely more than one way to do these. So if you are working these out on paper yourself or you go back and try and do them again, there's going to be more than one way. We've learned so many reactions that there's almost always going to be more than one way. All right, 2 more. So first one, actually, let's do the first one. We'll do them in order. So 1, 2, 3, 4. I would originally assume that that would be carbon 1 because that's where the alcohol is bonded. 1, 2, 3, 4. But that doesn't quite make sense because we wouldn't know how to add a methylon just to the end of a chain. So that's probably not right. So instead we could say just 1, 2, 3, 4. And then based off of that, we need to add an ethyl group. We need to add this propyl group and then eventually this alcohol group onto that chain. So this does use some reactions from last chapter as well. We can't just use a Grignard reagent because it's not symmetrical. So we can't add on 2 of the same groups. We need to do 2 different things, 2 different reactions. So if we start with our acyl chloride, how could we add on just that ethyl group, but keep the carbonyl in place? So really we would want to do that.
I'm thinking we just do 1 Grignard.
We can't just do 1 Grignard because it's so reactive. So the alternative to that is the Gilman reagent. So the Gilman reagent is our ethyl group that we're adding on with copper and lithium. So I'm going to put its name here. But essentially the result is 1 Grignard reagent, but that's not the actual like mechanism or reagent, but that is what we're creating here. What about that other group? So we still need to add on that 3 carbon chain and then eventually that alcohol. That alcohol, this oxygen is not the same oxygen that we already have bonded on. And we know that because of which carbon it's attached to. Our alcohol is not attached to carbon number 1 anymore. An acyl reaction, then reduce the ketone. And I'm not sure I know what you mean when you say an acyl reaction. So I'm going to remind you of one because what I have in my notes might be a little bit different than what you guys are thinking. What I wrote in my notes is the Wittig reaction. So if you remember when we talked about this, we have a carbon double bonded to a phosphorus that has 3 benzene rings attached to it. And then on that carbon, we're going to have a hydrogen and then something else. So in this case, we would want to have 2 more carbons because that's going to create our full 3 carbon chain. And so then we have that. Actually, let me change the angle so it looks the same. We have that. And so both of these, the Gilman and the Wittig, are very good reactions to add on carbon chains. And then to add on that alcohol, we're going to add on an alcohol using an anti-Markovnikov reaction because we're adding it on to the less substituted position. So that's our hydroboration. So BH3, THF, hydrogen peroxide, hydroxide. I think I have everybody in there. Again, there would definitely be more than one way to do this. But I wanted to make sure I showed those 2 reagents so that you don't overlook them or forget about them because they are really, really powerful ones, really useful ones. All right, we are at time. We will chat about this last one on Wednesday or whatever else you want to talk about in kind of prepping for the test. But yeah, that is it. So go click on the other link. Let's talk about some lab stuff. Thank you to oh, of course. Let me pull it back up, Justin. Oh. There we go. Sorry, went black on me. That top one is a little heavy. It would definitely have been like a challenging type problem for sure, because it's a lot of carbon skeleton changes, and anytime there are some carbon skeleton changes, it makes them more difficult. So understandable. Okay.